So it seems it is time to start. I would like to welcome everyone for joining this second session of 6G workshop by ICT-52 projects. In this workshop, we are going to have an overview of 6G radio enablers for communication and sensing applications that will be that has been covered in different EU projects. So we'll have 5 presentations from different projects, including Hexa-X projects, 6G brain projects, MARSAL, REINDEER, and RISE 6G. And we will cover different type of components that would enable future radio networks, including distributed MIMO, intelligent surfaces, and also modeling and technologies to enable sensing and many other different enablers for future networks. By this, I would like to invite Henk for starting the presentation from Hexa-X project, please.
Thank you, Hamed. Let's see if I can share my screen. Good. Can you confirm that you can see the slides in the correct mode?
Yes, the slides are clear and your voice is clear.
Okay, thank you. That was the most difficult part. Good, then let's start. So welcome to this presentation by Hexa-X. My name is Henk. I'm from Chalmers University of Technology in Gothenburg, Sweden. And I will talk about models and measurements for localization and sensing within Hexa-X. So the motivation for this work is that several of the use cases envisioned for 6G exceed the capabilities of 5G, in particular for localization and for sensing. And the vision for 6G is that we will have one system with a triple functionality, not just communication, but also localization and sensing built in. And this will be built in from the start, not just as an add-on later. The figure here on the right shows a kind of motivation of the use of 6G for these kind of applications. On the x-axis, you see location uncertainty. On the y-axis, different deployment regimes. And then the vertical lines, they represent different use cases. And then finally, the different blobs represent different radio technology. So you see, for instance, that GNSS can support a variety of accuracy levels, but is limited to outdoor environments. And then you see 4G, 5G, ultra-wideband, and finally 6G, which is intended to then enable very extreme use cases requiring extreme accuracies for positioning and for sensing. And so today we will see about the work that is being done in Hexa-X towards this. The goal in Hexa-X is twofold. So on the one hand, we want to explore the technological advances in communication systems, both within and outside of the project, to support localization and sensing, in particular for the sub-terahertz bandwidth carriers. And then finally, we also want to use this location and sensing information to improve existing communication, such as communication security, but also to unlock new applications. So this subtle interplay between location information, sensing information, communication is something that we explore. So this is the motivation for the presentation. Now we go to the outline. So I'll present a very brief background on localization and sensing. I understand that many people in the audience maybe are more focused on communication, so it's good to know some basics. Then I will talk about some initial work that we've done last year, mainly focusing on performance indicators, requirements, and gap analysis. Then I will briefly list what we see as the main enablers for high accuracy localization sensing, as well as some of the important challenges. And then I've handpicked or cherry-picked some individual studies within Hexa-X that we're doing on localization sensing. And then also I will include some results from our over-the-air demonstrations. Finally, I will wrap up with the conclusion outlook. So first of all, the background. So I want to settle our terminology first of all. So when we talk about sensing, we typically mean radar-like sensing, and this then breaks down into separate paths. On the left side, you see something called bistatic sensing, and on the right side, you see monostatic sensing. In bistatic sensing, there's a separated transmitter and receiver, and then in the middle is an object. The transmitter would then illuminate the object, and the receiver would get the observed signal. And then by combining information from transmitter and receiver, hopefully you can map the environment. And the transmitter and receiver could be base stations, or one of the two could be a user device. Monostatic sensing is something different. In this case, the transmitter and the receiver are co-located and typically share a common clock. So this is an example, for instance, with an automotive radar, which emits a radio signal. It scatters over the environment, goes back to the transmitting radar, is down converted, and then this radar can build up, for instance, a range Doppler map. These are two different modalities of sensing, but they both involve sending a known signal and then processing it to figure out where objects are in the environment. If you accept this definition, then localization is a kind of a special case of bistatic sensing, in which the user device has an unknown location. The typical way of doing positioning or localization in 5G is to use time of arrival. So this is shown on this picture, where your user device broadcasts a signal, which is then captured by several synchronized base stations, which compute so-called time difference of arrival measurements. This can then be complemented with angular information. For instance, if the base station sends directional beams and the user measures the power corresponding to those beams, this provides you an angle of departure and downlink measurements. And then you can combine those measurements in different ways. You can do only time-based measurements, only angle-based measurements, or any combination of the above. As a final part of the background, I want to just spend one slide on so-called integrated and joint sensing and communication. There's been a lot of hype on this, and I think maybe there's some also ambiguity about what different terms means. So one thing is something called joint communication sensing, and this is mainly considered from the monostatic sensing perspective. This is what's shown on the figure on the right, where a transmitter is emitting a waveform, a communication waveform intended for a communication receiver, but at the same time can process the backscattered signal to form an image of the environment. In this case, we're using the data for sensing. We have a common clock because we're doing monostatic processing. And you could argue that in some sense, we get the sensing capabilities for free. And this is truly joint communication sensing, doing it with the same devices, with the same waveform over the same time frequency resources. When you try to extend this to a bistatic scenario where you have a remote transmitter and receiver, then questions pop up, such as, is the data known by the receiver or not? And do the transmitter and receiver share a common clock? And these then form interesting research questions. A slightly broader perspective is when you think about integrated sensing and communication, where communication and sensing interact, but they don't necessarily need to be done at the same time over the same time frequency resources. And then you can ask yourself, should we share the same devices for sensing and communication? And I think it is a possibility that there could be dedicated sensing beacons or positioning beacons, and still you can have integrated sensing communication. A second question then is, should you use the same waveform? Should it be the same OFDM-based waveform for sensing communication? Not necessarily, but it could still be integrated sensing communication. And then finally, should you share the same time frequency resources? If you answer yes to all of the above, you have really joint communication sensing. But if you answer no to some of those questions, you still have a form of integrated sensing and communication. So I think the field is much broader than maybe what is typically been limited to joint communication and sensing. Good. With that background, we now move on to some of the more specific work done in Hexa-X. So our first work was on performance indicators for localization and sensing. Just as in communication, you have a variety of performance indicators, you also have this for localization and sensing. These are some of the indicators that we've considered in our work, including localization accuracy, also orientation accuracy. So we want to estimate the 3D orientation of devices, the latency, so the time between a positioning request and the information being available, the availability in time and space, and the scalability in terms of number of devices. And then with these metrics, we've done a gap analysis. And some of the results of this gap analysis are shown here. And this is from a recent Vehicular Technology magazine paper. So for instance, I will only focus on the picture on the left. It's a very busy picture, but it tries to summarize many things. So on the x-axis, you see the accuracy requirements of different use cases, and on the y-axis, the maximum tolerable latency. You see these diagonal lines, which correspond to high speed. And this is because a use case with a certain accuracy requirement and higher velocity has a more stringent latency requirement. And then you see all the different kind of blobs, and they represent all the different use cases that we're considering within our Hexa-X work package. And they vary from extended reality all the way down to smart utilities, patient tracking. The different colors represent different availability requirements. And then you see also horizontal and vertical lines. The horizontal line is the 5G capability in terms of latency. The vertical lines are the 5G capabilities in terms of accuracy. So only when you have a latency which is above the horizontal line or an accuracy requirement to the right of the vertical lines, you can be supported by 5G. So we see that many of the use cases considered cannot be supported by 5G, which then motivates the work that we do towards 6G and Hexa-X and other projects. Now, to achieve this high requirements, we rely on a variety of technology enablers. I just want to briefly list these. So, among the enablers, we have the following 8. So the first one is that we will have a variety of carrier frequencies. It will not only be FR1 and FR2, but also sub-terahertz bands. And all of these together, they provide high accuracy, localization, and sensing. And I think it's important that all of these bands should be combined in a smart way. By combining those bands, you will have large aggregate bandwidths, typically above 1 gigahertz, which provides extremely fine delay resolution, similar to what you would have in a high-performance radar. Next, when we consider these very high frequencies, we need a large number of antennas to overcome the path loss. And this large number of antennas will need to be placed both at the infrastructure side as well as at the user side. And this then allows you to estimate the 3D orientation of the user. So we move on from 3D positioning in 5G to 6D positioning in 6G. Other enablers are the use of side link for relative positioning and for radar, distributed self-free massive MIMO with phase coherence, which provides extremely large aperture around devices and would be a new dimension to explore localization and sensing. As I mentioned before, the integration of sensing, localization, and communication, typically called ISAC, which is much more than just joint communication and sensing. The 7th enabler is the use of artificial intelligence for solving many problems at different layers of the protocol stack. And finally, the use of intelligent surfaces or reconfigurable intelligent surfaces to shape the environment to improve communication, but also positioning and sensing KPIs. With these challenges, with these enablers come also some important challenges. So the first challenge that we've experienced is the hardware impairments. So first of all, hardware impairments are more severe the higher we go up in carrier frequency. And secondly, we have observed that the hardware impairments are more severe for localization and sensing than for communication. Because for localization and sensing, we care about the details within the channel, the angles and delays within the channel, rather than the end-to-end channel. A second challenge, which is often forgotten, is that when we want to have extreme performance, we want to have centimeter level accuracy, we need extreme calibration. We need to know exactly where our reference points are. We need to know exactly the tilt of antenna panels and so forth. And a final challenge is that it's hard to meet all of the requirements at the same time. It is really hard to have very high availability, very high accuracy, very long range, very low latency all at the same time. So this requires smart and adaptive processing. With these now enablers and challenges in mind, I go on to some of the selected studies within Hexa-X on localization and sensing. But we have a lot of work going on, which you can read about in our past 2 deliverables, as well as our upcoming deliverable in April. So I've had to just cherry pick a few. Nevertheless, despite my cherry picking, we have a somewhat coherent framework of dealing with these problems. So what we do is we use channel and hardware models both from within and outside our project. And then we apply them to, first of all, model-based localization and sensing, and where we see here on this horizontal line, the kind of different processing steps that we go through, including signal design, channel parameter estimation, for instance, angle and delay estimation, and then estimating the state of the object in the environment and doing performance evaluation. We similarly have an AI-based track on localization and sensing, where we use machine learning and data-driven methods to solve similar problems, typically in the presence of hardware impairments or cases for which we don't have a good model. And then finally, we also use location map information for supporting location-aided services, including communication and security. So we have all of these 3 tracks. Today, I will only focus on the first 2 tracks and just present some selected studies. A first study is the impact of hardware impairments. So what we want to study is we want to understand to what extent do the hardware impairments affect localization, and under the same performance and the same parameters, how much more is localization affected than communication. So the figure on the right shows here a typical processing chain. You have a transmitter, a receiver, and in between a channel. And in colored blobs is highlighted different hardware impairments. And then we can process the received signal by estimating channel parameters and then estimating the location orientation of the device, for instance. Now, under a certain scenario, what you can, for instance, see in the figure on the middle is this is the communication performance. So you send 16 QAM, and if you have sufficiently high SNR, you will receive this kind of clean-looking 16 QAM signal. But then under those conditions, you could still have severe degradation of localization and sensing. That's what's shown in the figure on the right, showing on the x-axis the transmit power, on the y-axis the positioning performance, where lower is better. And we see that there's a kind of flooring effect. So when you go to high transmit powers, the hardware impairments start to dominate. They will be much more dominant than any of the other impairments in the system, including the background noise. So they will limit the performance that you can get. And this is one of our important studies, which we're both doing theoretically as well as through the experimental setups. A second study, this is more focused on AI. Here we're looking at AI for non-radar type sensing. In this case, contextual sensing, where we want to detect the activity of humans in an environment. So we're sending waveforms, we're receiving those waveforms at receivers, and then we're applying AI to figure out, are the persons in this environment present, and what is their state? So their state could be walking up or down, sitting, standing, or laying down. And we use both traditional AIs, for instance, support vector machines, as well as more modern AI tools such as deep learning, which don't require feature engineering. And then we see what kind of performance we can achieve. And for instance, here in this example, we see that with 6G systems, we can attain very high accuracy in terms of human activity detection. So this could be a non-intrusive way to monitor, for instance, elderly or people who have certain neurological disorders. The third study, there's 4 studies, so this is the third one, is how sensing can be incorporated in a communication network. And we realized early on that while we know that there's monostatic and bistatic sensing, that monostatic sensing is very challenging because it requires full duplex capabilities, for instance, at the base station or the user, which is expensive and also power hungry. On the other hand, bistatic and multistatic sensing are maybe easier to realize, but then have limitations in terms of the data that can be shared between the transmitter and the receiver, as well as the synchronization. And we've performed several studies, in particular focusing on higher frequencies above millimeter wave. And what we found, for instance, is that the sensing accuracy and coverage are in a trade-off. When we go to these higher bands, we'll have better accuracy because we have more bandwidth and more antennas, but we have less coverage. And the figure on the top right shows, for instance, an example using FR2 waveforms, how well we can separate objects, in this case, 2 objects with different range and different speed. We've also studied the resource allocation aspects, as well as overheads associated with localization and sensing. And this is something important that we're continuing to study. A fourth study deals with energy efficiency. And this is here now a study that talks about how can we use location information or sensing information to improve communication. And one of the concepts used here is the so-called channel knowledge map, which is illustrated on the top right. And the idea of a channel knowledge map is that we would have a database which relates individual positions to some kind of channel state. This could be the full channel matrix corresponding to a certain base station, or it could be something more simple, for instance, the involved transmitter or receiver beamforming and precoders and combiners that you would use in that location. And then by using this channel knowledge map, you can reduce the overheads, and this would then in terms results in improved energy efficiency. So that's what the figure on the right is showing as a function of the base station transmit power. On the left figure, the energy efficiency, and on the right figure, the spectral efficiency. And we see that with this channel knowledge map, we can do much better than training-based techniques, which require transmit and receive beamform sweeping and almost matching perfect CSI information. So this is something very promising for reducing overheads and then overall improving energy efficiency. A lot of the work I talk about so far has been focused on more theoretical analysis and system simulation. We also have over-the-air demonstrations for localization sensing towards 6G. So this is one of our setups where we have a platform for integrated communication localization sensing. And we use this both as a proof of concept, but also to verify simulation results and test different use cases. And for instance, we would analyze different waveforms, how well they can be used for localization sensing, or even optimize waveforms for localization sensing compared to waveforms optimized for communication. The figure on the right shows the hardware board as well as the connected FPGA. And then the three snapshots on the bottom show the bistatic operation here at 69 gigahertz. So there's a transmitter on the right, a receiver on the left, and we're sending signals from the transmitter to receiver. And these are then processed through beam sweeping, in this case, to estimate the angles. And then also we look at the channel impulse response to estimate the delays. So we see here on the left that there are different objects in the environment. One corresponds, actually the strong object corresponds to the reflection from the wall, and then the weak object corresponds to the metallic hat worn by this person. And when the person is moving, we see that the different targets in the environment are changing, and we also see the changes in the impulse response. We have a small video on this. I don't know how well this will work over streaming over Teams, but we can try this. It is just a little bit more than 1 minute. So this is the same setup I talked about before. This is the transceiver system with multi-antenna processing and analog beam steering. The FPGA doing the processing, lots of cables to make this work. This is the same setup as before. We're using here a DFT spread OFDM, so this is the same as an uplink 5G waveform. We're processing the waveform here. This is not non-real time. We need to do some initial synchronization. And then we see that we can correctly recover the communication waveform, in this case, to get the 16 QAM data with high SNR in this case. Same for OFDM, so we can deal with a variety of waveforms. We can also deal with a variety of transmit precoders and receiver combiners. So again, we have a cleaved waveform also for OFDM. And these are done the same examples for doing the beam sweeping and then figuring out where the objects are in the environment. And we see them here in angle domain as well as in the range domain. This was just a small teaser of our experimental setups. If you want to see more about this, you are welcome to visit EUCNC in Sweden, where the final demonstrations will be presented. This leads me to my last slide, so conclusion outlook. So in the 6G system, we have this vision where localization and sensing will no longer be a byproduct. It will be something inherent and integrated from the beginning, and thus it must also be one of the design targets. Many of the use cases that we've identified in Hexa-X require high accuracy localization and sensing, and require the integration of localization and sensing in the 6G system. Within Hexa-X, we focused on methods, signals, and protocols to support localization mapping on the one side, and also then location and sensing enhanced services. So communication, but also security, and for instance, non-radar-like sensing, including, for instance, pollution and weather monitoring. We are currently working very hard on our last deliverable, which will be published in April, which provide our final models, measurements, and performance evaluation, as well as novel signal designs and evaluation of location-based services. So we invite you to look at our deliverables, to visit the Hexa-X website for more information. And this ends my presentation. Thank you.
Thank you so much, Henk, for this presentation. And there is already a question on the chat, so regarding the 6G region, related to sensing and positioning and how it would meet the requirement for extended reality. Is there any thoughts here?
Yeah, so extended reality is actually our most difficult use case. So because it requires extremely high accuracy, extremely low latency. At the same time, you need to push through a lot of data. And I think this is somehow will be one of the showcases. This is something that we want to demonstrate, but this is not something that I think within Hexa-X that we will be able to do. This is more for Hexa-X2, which is starting right now. So I agree. It's the most challenging application. I don't have the answer to that yet.
Yeah, thank you. And the example that you demonstrated related to using sensing for communication purpose is interesting. How these new services would contribute to the sustainability of the future networks. So this kind of capability is would enable new opportunities to improve the way that we have been doing communication over networks, and I would expect several of such kind of use cases to appear in the coming years, and as we have more and more such capabilities in the networks.
Yeah, definitely. Especially when we go to these higher frequencies where everything becomes almost geometric, and the location information will be really instrumental to point to the right direction if you know where things are.
So would we expect such kind of performance gain to be observed in millimeter wave already, or how much of it could be realized in millimeter wave?
I think already a lot could be realized in millimeter wave. This is something that's been, I think, underutilized. If you have a large base station, that especially millimeter wave, that needs to do this beam sweeping procedure, if you know a priori where the user is, you could just immediately direct the beam towards the user. The beams are sufficiently broad to cover the user with some uncertainty, but they're still so narrow that you need to sweep a lot if you don't know anything a priori. We've done experiments together with Ericsson on this, and you can have enormous reductions in overheads by doing this kind of procedures.
Yeah, thanks a lot. So there seems lots of opportunities in this domain to work on. If there's any other questions, so we have still 3 minutes. So if not, may I ask about you raised a concern regarding the hardware impairments. So may I know which of the hardware impairments would be more challenging for this type of use cases among different components that we?
I think probably the main one is somehow the calibration. When you think about the current base station using beams, you don't need to calibrate exactly where it is or what does each beam look like. It's enough that beams have a rough direction to enable the communication. But for localization, we need to know exactly orientation of the panels. We need to know exactly the shape of each beam as a complex response. And this is typically not done. And this may require per device calibration, which is something extremely expensive and typically not considered by the operators.
And you also have had example related to the AI that showcase that how AI could be of benefit here, and it seems that there are also some opportunities there to compensate for this type of impairments.
Yes, exactly, because AI can learn over the wireless channel, including all the impairments. It can somehow automatically mitigate those impairments, provided we have enough training data, of course. That is then the bottleneck is then shifted there.
Yeah, great. Thanks a lot, Henk, for a nice presentation discussion. So
thank you, Haman.
I think by this we can go to the next presentation by 6G Brain project. Diego, if
hi, can you hear me?
Hi.
Yeah, good. Nice to be here. Let me share the.
Yeah, please feel free to share the slides.
Is it right, or is in the right mode?
Yes, the slides are clear. Yes.
Okay, good. Then let me look for a pointer. Okay, well, thanks. Do you mind if I switch off the video just because of the bandwidth, or?
Yeah, sure. Then I also switch it off. Then.
So thanks. I am Diego Dupleich. I am from Fraunhofer Institute in Germany. I am the work package 3 leader and from 6G Brains, and here we deal with let's say the channel model of our project and also the physical interfaces. What I'm going to present now are multiband channel measurements and ray tracing modeling in industrial scenarios here. So Let me see if I can switch to the next slide. This is the outline. I will start with a little motivation on why we are following this channel model approach. Then I will show you the methodology and the workflow we are following, and I will conclude with some conclusions. Yeah. So we are talking about Industry 4.0, where we have multiple requirements on broadband, on reliability, on the massive machine communications, where we have a high density and coverage requirements of over 1 million IoT devices per kilometer square, where we need high accuracy of a centimeter level for localization and millimeter level also for augmented reality, as we hear from the previous presentation as well, which is very challenging to achieve. We also have requirements on low latency for real-time remote control of machines, and also high data rates in the sense of, for example, real-time analysis of video or for collision avoidance of AGVs and drones. All these requirements are difficult to fulfill with a single radio interface. For example, with a low at sub-6 GHz, we can have a very high reliability. There are some works where you can find that with massive MIMO industry scenarios, you can achieve a very good reliability. But of course, in terms of broadband or data rates, we are limited because of the saturation we already have in the spectrum. On the other side, we can use millimeter waves where we can have high data rates, but reliability is also a problem there because you have higher obstruction loss and penetration losses. So you have a lot of regions where you can have some shadowing. And also if you go to higher in frequency, even to 4 terahertz, you can latency also becomes an issue because you need first to point your antennas or the gain of your arrays in order to have communications, and this introduces some latency. So the idea is to have an heterogeneous network where we can use the different, let's say, properties or benefits of the different radio interfaces in order to cover all the requirements. An example of what we are analyzing here, is this, where we can have a mobile user in the factory. Then we can have some access points at sub-6 millimeter waves or terahertz, other access points at millimeter waves or optical wireless communications as well. We can have some access point inside of machines at terahertz, where you have a higher data rate requirements. And of course, then you can also have integrated access and backhauling terahertz links in order to communicate all these access points wireless and to have a more flexible deployment of the communications network. The idea is that you can have, for example, a sub-6 link with this AGV or this mobile user. You can also, if you need higher data rates, you can use a millimeter wave link. Now the research question here is, can we use the same link as we have at sub-6? Do we still have let's say a good channel if we use the same pointing directions? These are things that we can investigate. Also, we can have, for example, a millimeter wave that is in line of sight in case that this link at millimeter wave doesn't work. And then, as I mentioned before, you can use terahertz for backhauling. So the idea is that if we want to test all these different applications and use cases, we need channel models that can address these issues. And the requirements of these channel models are basically that we need a spatial consistency, intraband and also interband. For example, if we have 2 mobile users that are closely located, or the same mobile user that actually change position, we know that actually the scatterers or the reflections come from the same scatter, so we need a correlation between the propagation properties. And also this has to be if we have different bands. So we need to be able to simulate this correlation over frequency as well. And of course, we need also very accurate information on the angles of arrival and departure, because we need to test beam steering and beam forming applications If we talk about ICAS or ISAC application as well, this is also a need. And yes, in terms of factories, if we want to apply any kind of digital twins applications, we need this kind of properties in our channel model. So this is basically the motivation on why we go into this direction. If we look at channel models that cover this wide spectrum of requirements, also of course of physical models, we usually have either deterministic or stochastic models, or some hybrid ones. The trend is to go into a hybrid model where we can have some components which are deterministic, and then we can introduce stochastic components in order to complement this. This is basically what we see here. This is where we locate our channel model, where we have the big part or the major contribution is going to be deterministic, but we are going to complement it with the stochastic components that we cannot simulate from the ray tracing, right? So saying this, I will show you the workflow we have been following in the project. We have done in different scenarios simultaneous multiband measurements together with 3D laser scans of the scenario. So then with the 3D laser scans, we have obtained a CAD model, and from there a ray tracing model. Then we have parameterized, we have parameterized the CAD model with electromagnetic properties in order to obtain the ray tracing model. You can find more details of this in the deliverable 3.1 and related to the multiband measurement systems in the deliverable 3.2 of the 6G Brain project. Then we have conducted some simulations in the same positions as we did the measurements. And the idea of this is to compare the measurements with the simulations, of course, considering what we want to identify is first we know the limitations we have in the simulations, that we can only simulate specular components. So in the measurements, of course, we are going to have more components. So the idea is to validate these specular components from the measurements. Then part of the project is as well to extract stochastic parameters from the channels, the one that we cannot cover with the deterministic or with the ray tracing simulations, and then be able to combine both of them into the model, which is in the deliverable 3.4. What I'm going to show you now is this part of the workflow. We will start with the ray tracing model. What we have here is the model in the Bosch plant in Bleichach in Germany. Yes, basically the size of the hole is about 42 times 46 times 11 meters. And we have, as you can see, a lot of objects and details. Here we have conducted two different scanning processes, one for the macrostructure, and then with a handheld scanner we have scanned the machines that you can see. I don't know, sorry, you cannot see it here, but in the production lines here you have a lot of machines, and we have scanned all of the machines and then introduced them in the macrostructure in order to have a very high a model with a lot of details, right? So then we have another model which is smaller. This is 6.48 times 10 times 6 meters. This is in the facilities in Ilmenau. And the idea is we follow the same procedure from a point cloud to CAD and then to a ray tracing model. And what we want to do actually is to compare the measurements with the model to see if these models are representing accurately the reality. In terms of measurements, we have two different approaches as well. In the Bosch factory, we conducted a multiband measurement. That means that we measure simultaneously at 6, 30, and 60 gigahertz. We use a bandwidth of 5 gigahertz in the different bands. That's why we also cover here the sub-6 spectrum. The idea to use such a large bandwidth is to have the same delay resolution in the different frequencies. We have used the transmitter high gain antennas, dual polarized with 30 degrees half power beamwidth. and at the receiver, dipoles that allow us to capture, to speed up the process and capture more measurement positions. We have used at the receiver 2 different antennas that are located in different positions, but we repeat the measurements, and then we have the channels at the different frequencies in 2 different positions. The idea is that we rotate mechanically the antennas, and then we can capture in different directions the channel impulse response in different frequencies, and then we can combine them, and we have the, let's say, the quasi-isotropic or synthetic omnidirectional characteristic of the channel in the different frequencies. Then we can compare the channels, right? So this is a picture of the setup in the measurements, where we have in red are non-line of sight positions. These positions are behind this big metal structure. Here you have a production line, here you have another production line, and these positions are in between these 2 production lines as well, so they are in non-line of sight, and all the green ones are pure line of sight measurements. You can find more of this in the deliverable, also in the papers. When we look at the results in the different bands, these are measurements. This is line of sight position when the receiver is in front of us. You can see that we have a high correlation in the different bands. This is obvious because of the line of sight component. But when we go to non-line of sight, when the receiver is behind this big metal structure, we can still see that actually also we have a high correlation on the power angular spectra. This is basically because the signal goes here and bounces, and then you hit the receiver from that part. But still we have a high correlation. When we look at the power delay profiles for the different receiver positions over the line of sight, we can see here the line of sight component in the different bands, and also we can see that the deterministic or the specular components are present in the different bands. This is all from measurements. So we have a highly correlated channel in terms at least from the dominant components. This is a single snapshot where you can also see for the same position sub-6 30 and sub-6 and 60. And again, you can see that the dominant components are in the different bands, especially these ones here. And also we observe that when we increase frequency, the DMC power is also decreasing. So these are just some analyses to compare the different bands and to see what are the similarities and the differences. We have also now extended these measurements for this for quad band. In this case, what we analyzed are 3 different RF bands, and also we have included optical wireless. We analyzed 6, 70, and 300 gigahertz. We have used high gain antennas, dual polarized at transmitter and receiver. And as you can see in the transmitter and receiver, we use high gain antennas, so we rotate at the transmitter and receiver. Unfortunately, for the 6, we still use 30 degrees half power beamwidth antenna because of the size. And of course, as you can see in the patterns, that will introduce some bias that we will later see, but still allow us to find some similarities and differences. The results on optical wireless will be presented in the deliverable, but I didn't include them here in this presentation. We have also done some calibration, verification measurements, and you can find all these in the deliverables. So for this measurement campaign, this is the small machine room in Ilmenau, where we have a CNC milling room machine. We have this is the view from the transmitter, from the channel sounder. We have a line of sight position and a non-line of sight position. I pick up only 2 in order to show more details on the measurements. This is again the view from the line of sight position, and you can see that the non-line of sight position is behind this machine. Yes, and then when we look at the measurements, and for the line of sight case, you can see this is sub-6, this is 70 and 300. As I mentioned before, because of the wider pattern of the antennas at sub-6, we see a more crowded power angular spectrum, but we can still figure out that the main scatterers, which are this is the line of sight, and this is a reflection on the machine, the reflection on the wall. These are other reflections that we see at low frequencies, but at terahertz, we don't see them, mostly because of the dynamic range of the measurement system. But let's say the dominant components are visible in both cases, right? At sub-6 millimeter waves and terahertz. This is a power delay angular profile again, where we can see the similarities on the channel. Sorry, we have the line of sight, then we have the reflection on the machine, and then we have some scatterers that we see them at low frequency, but not at higher frequency. But since they are arriving late, most probably this is because of the dynamic range of the measurements at 300 gigahertz. When we look at the isotropic power delay profile, this is combining all the power delay profiles over the different directional scans. We can see again also we have the line of sight component, then we have the reflection on the machine, and you can see that most of the scatterers are visible in the different frequencies, and they correspond to a specular path. Of course, when we go up in frequency, we still see them, but when we go the late arriving path, we cannot see them in terahertz, but this is mostly because of the measurement and the dynamic range of the measurements. When we look at the non-line of sight position I mentioned before, we see a more scattered or a crowded power angular spectrum. This is because we don't have the line of sight component, and we get more reflection from, in this case, we have a double bounce reflection here on the cupboard and the door, and then arriving to the receiver from behind. Then we have a single bounce reflection on the wall, on the doors, sorry. And we have other components on the wall. Then we have high order reflections on the different walls, and so on, so on, and so forth. What we can see them again, these components are visible in the different frequencies. We have here a big cluster or big components that are visible at lower frequencies, but not at higher frequencies. And because of the angle of arrival and departure and the delay, they correspond mostly to diffracted components and reflections on the local area of the receiver. This is what I mentioned before. I mean, this is what you see here is the delay in the x-axis, and you can see that these clusters are visible at sub-6, 70, but not at 300 gigahertz. But all the other ones are visible in most of the frequencies. Here we have some components that are not visible at 300 gigahertz either, but at 70 and sub-6. Again, when we look at the power delay profiles, we can see again common path in the different bands. Not here, we don't see here the 300 gigahertz, which are the early path, but we see all the other paths, we see them in the different frequencies with different amplitudes, but they are visible. So I will speed up, and we have the ray tracing validation now. And that means that we are going to compare the measurements with the simulations. Of course, the simulations in the ray tracing, we get deterministic path, we get very accurate delays, angle of arrival and departures, and the equation looks like impulse of deltas, as you can see here. But if we want to compare this with measurements, I mean, this is not possible, because in measurements we include the antennas. We have also limited bandwidth. That means that if we have two closely located multipath components, they are going to interact, and they can introduce fading, making that, for example, these two guys here look bigger or smaller, depending on how they combine. So what we do is we introduce in the ray tracing simulations the antenna patterns we have used for measurements, and also the bandwidth we have used for measurements. As you can see, when we introduce the antenna, we already killed a lot of multipath components. And then when we introduce bandwidth, and then we use the different scans, you can see that actually we have the effect of introducing fading in the overall result. Yes, this is the comparison of ray tracing in the big scenario at Bosch, where we have in the non-line of sight measurements, we were able to see these diffracted reflections on the pipes here components. We were also seeing them in the ray tracing. We have the reflection here in the column. It's also seen in the simulations and in the measurements, and also this reflection here, which it corresponds to S4, which is a reflection on the stairs. So we are kind of happy with the results we obtained. And when we go to the model here in this machine room, we are also, when we superimpose the picture from the channel sounder with the simulation from the ray tracing, we can see that we are able to catch the reflection on the wall that we saw before. This is the line of sight component, the reflection on the machine. We have here also in the simulations a reflection on the crane. We're not able to capture them in the measurements because we have only measured in azimuth, not in elevation. But when we overlap the power spectra of the measurements, we can see actually that we have a good a good match between the measurements and the simulations. This is a view from the receiver point of view, and then again we have a good accuracy on where the signal is coming from. And this is the power spectrum, again the comparison. This is the simulation, this is measurement at 300 gigahertz, and we are able to really see the line of sight and the most dominant components. Also, it's interesting when we decompose, since we did dual polarized measurements, when we decompose the measurements in polarization, the reflection on the machine is only visible in the vertical to vertical and not in the horizontal to horizontal, or it actually follows below the dynamic range of the measurement system. And the ray tracer also is mimicking this propagation effect very well in terms of we have a stronger component in the vertical than in the horizontal polarization. When we look at the power delay profiles, we see also agreement in most of the paths. I mean, we have common paths between measurement and simulation. They have different amplitudes, but we were able to track them. So we need to adjust still the electromagnetic properties of the materials. Then we have some paths that are only visible in the measurements. And this is because of course, the lack of or the limited number of objects in the simulations or in the map. And we have some paths that are only visible in the simulations, and they mostly correspond because of wrong electromagnetic properties of the materials, or also when we simplify, for example, if we have a round column and it's simplified to a polygon, it creates shapes that actually we don't have in reality, but creates specular components in the simulations. When we look at the non-line of sight, we still, again, when we compare the measurements with the simulation, we have a very good agreement. In the simulations, we still see that we have these components that corresponds to the diffracted components are still simulated with more power than they actually we measure. When we also we have analyzed the polarization, and we don't see big differences between measurements and simulations. But when we analyze again, I mean the power delay profile, we can see that these components in the simulations, in the measurements, are visible at low frequencies in the simulations as well. But yes, but it's also pretty well captured in the sense that we have a higher power at sub-6 than at millimeter waves, and it's the same what happens here. And again, we have common path, simulations and measurements, and then we have paths that only we see at measurements and paths that we only see in the simulations. But this requires further analysis. But of course, we will never get a perfect match. And this is from, yeah, this is what I showed before, but for the non-line of sight case, where we can also see where most of the paths are coming from. Also, it's interesting to see how in the ray tracing model give us a lot of paths arriving from the light holders here, and also from the crane, as we mentioned before. So yes, this is all. The conclusion is that we have seen that most of the strongest and dominant paths are visible in the different measured bands. We have seen that paths are only visible at lower frequencies. The early arriving paths, mostly because of diffraction and low penetration losses, and the late arriving path, and mostly because of the limited dynamic range on the measurement system. This is comparing over frequency. We can see a very good picture of the geometrical properties of the scenario from the propagation properties of the multipath component, and this is what we are going to exploit for ICAS, localization, and also other applications we are testing in 6G brains. Future work is the calibration and adjustment of electromagnetic properties of the material in order to fit better the measurements with the simulations. So this is all. Thanks for your attention. I hope it was interesting for you, and you're welcome to make questions.
Thank you so much, Diego, for nice overview. So far, there is no question on the chat. So if there's any question, please feel free to raise. We have a few minutes. So certainly, channel modeling is an important activity towards evaluating and assessment of different technology components that are going to be appeared for 6G. And here I have a question regarding the scenarios that you have developed channel models. May I know in what extent the mobility has been considered in the modeling in the industrial environments and how it would affect possibly the channel models there?
This is a good question. Yes. Well, because of the measurement capabilities, as you know, we cannot we use high gain antennas, so we cannot capture, let's say, the spatial properties and the mobility at the same time. So basically, on the measurements we rely on the spatial properties, and simulations we include the, let's say, the Doppler that we can have for different multipath components. But yes, it's of course, we are going to the direction of trying to enable measurements also for mobility, while you have also angular resolution. For that, we need antenna arrays, and it's still challenging for terahertz, and for millimeter waves still challenging, and for terahertz is still very on the early development. But of course, models have to consider, especially industrial scenarios where you have a lot of things moving around, and this is going to be one of the key aspects to see.
Yeah, thank you. And then regarding this non-line of sight scenarios in sub-terahertz cases, so is there any insight in what kind of range non-line of sight would be still an option for either sensing or communication?
Yeah, this is a good question. I mean, we have seen that because of all the metallic structures you have there, we were surprised about how you, even if you're non-line of sight, you can still capture a lot of multipath components from the environment. And I cannot give you an accurate number because I haven't looked in details on what is the range or distance you can cover, but in this scenario of, I think it was 6 by 6 meters, we were still seeing a lot of multipath components in non-line of sight. So this is something that I think is promising. I mean, the multipath components are there. Of course, you need to look where they are and point the gain of your antennas in that direction, but the multipaths are there.
Sounds interesting, and thanks for sharing the insights. So I think it would be very valuable across different projects that are working in these directions. Yeah, by this, I would like to thank you again.
Thanks you, and thanks for organizing this.
Thank you. And I think if there is no further question, we may go for a break. Yeah, there is a question so on the chat. So if you can see the question, then
the channel equation that you share, is it generalized or specific to that context? Yes, I shared two channel equations. One is related to the output of ray tracing simulations. Sorry, it's going to take forever to go back to that. And this is generalized in the sense of, sorry, I don't know if there is an E further. Yes, I mean the channel from the ray tracing is generalized in the sense that this is the channel pulse response of sorry, I don't know exactly in which slide it was, but yes, the channel equation was is a general in the sense of the ray tracing because it's a channel impulse response, and is for this context is only when you introduce the antenna gates and the bandwidth to emulate the measurement equipment, so you can make a more or a fair comparison between simulations and measurements. I don't know if that answers the question or.
thank you, Diego. So if there is no further questions, so we can leave the discussion here. And if there's any further question, please,
You can contact
yeah, contact Diego. And so I think we could have 30 minutes break, so we can continue the seminars by 3:15. See you soon. Hi, Sofie.
Hello, good afternoon.
Hi. Yeah, good afternoon. Welcome. I think we can wait maybe one or 2 minutes. So
Yeah, sure.
Should
I share my screen already?
Yes, please.
Hola. All right, I think that should be right now. Just let me know when you want me to start.
Okay, sure. Maybe in a from this project, please.
Okay, so thank you very much for organizing this very interesting and timely workshop and also having me here. So I'll be the first one to talk about some work we're doing in the context of the MARSAL project. So I'm not sure if most of you are familiar with the MARSAL project. So that's why I will maybe just share with you some information about what MARSAL is all about. So MARSAL is basically about resource management, and we want to manage both communication and compute resources. And we do that for 5G and beyond networks. So we have a very distributed architecture in MARSAL. So we have our researchers go from the core network all the way to through the regional edge to the radio edge. And what I will be talking about today is mainly linked to the radio edge, because that's where our research is focused on, or at least the research from work package 3 and what KU Leuven is doing in MARSAL. And as you can see here, I'll make my pointer a bit more visible, is that this radio edge is very distributed. So we have a lot of distributed access points, so it links a bit to self-free. So you see here distributed self-free coordination as a term. And you also see we have a wireless backhaul, so fronthaul. So we have a millimeter wave wireless fronthaul in our architecture. So the objectives of MARSAL, so we have 3 pillars. So one is a network design, where the main innovation is on the wireless domain. So in the wireless domain, we have the distributed processing for self-free. So there's lots of distributed processing for self-free happening, but in MARSAL, we are specifically mapping this on the ORAN architecture and we're studying what has to be done to make all these distributed processing possible within the ORAN architecture. And we're also focusing specifically on opportunities that come when we also have a wireless millimeter wave fronthaul. So the companies that we're working on mainly for this work are companies like Acceleran, IS Wireless, and Ferrotech. These are all SMEs working on millimeter wave or ORAN technologies. And I myself from KU Leuven, which is a research university located in Leuven in Belgium, not so far from Brussels. And we also work together with Intracom for this work package. In MARSAL, there's also a lot of work happening on this virtual elastic infrastructure design, which deals with the optimization of edge computing, etc., and network slicing as well. And there's also a lot of focus on security, but there will be other talks scheduled tomorrow to discuss all this. So I will focus on the radio access part. So first I will introduce to you from a very high level point of view, the ORAN architecture and how it links to self-free massive MIMO. Then I'll discuss a little bit the implications of all this distributed processing on the Fronthaul, and I will conclude my presentation by saying some words about millimeter wave. Voila, ORAN architecture. So here we have a figure from the ORAN architecture. So we have a user equipment, and then what you can see here is that ORAN basically disaggregates. So ORAN is about disaggregation, the baseband unit in a distributed unit with the real-time functions and a central unit with the non-real-time functions. Then the latter is also disaggregated into central unit user plane and central unit control plane. And you see also here in ORAN, what is very important is this real-time RIC with the XAPs. So the idea here is that you have some kind of resource controller that is running new applications, XAPs they're called in the ORAN terminology, which make all kind of new network functions possible. And you also see here the ORU is the radio unit, and one of the questions to address is how to split the functionality between this one and the ODU. Both focus on real-time processing, but depending on where you do certain things like channel estimation, precoder or receive beamforming, the computation of that vector or the application of that vector. Depending on that, you have different requirements on the control and the user plane in your Fronthaul, and you also obviously have very different performance for your users. So if we look into self-free massive MIMO, then the most simple way to look at it is you have a network with many access points distributed in an environment. You also have users, and typically it's assumed that you have less users and access points or antennas than the access points. And all the signals received by these access points, if you consider the uplink, or centralized into a big processor, a CPU, where all the signals are combined and the estimations are happening. Of course, you could argue that in self-free MIMO, this processor does not have to be necessarily centralized. You could also have distributed CPUs that work together one way or another. But I think it is clear that one has to decide how this processing should be organized, how to collaborate, in which order, and which information to share, etc., etc. So this kind of view, this self-review, naturally links to ORAN. Because we could do the central processing in the ODU and the OCU, we could do some processing in the ORU, and we could do the clustering, which means deciding which access points serve which users in the real-time RIC. So for MARSAL, we want to see how we can map this, what we call scalable self-free algorithms on ORAN, and our view of the self-free architecture looks a bit like that. So we don't have only one CPU, we have many of them, because we have a big network with many DUs and many CUs and many real-time RICs, etc. We have, of course, the radio units, we have a user equipment, and we do some kind of clustering. Ideally, we do what we call user-centric clustering, which means we start from the user and we decide which access points should serve a given user. That could mean that we have RUs or access points that are controlled by different DU that should collaborate together. So we call this inter-DU cooperation. And one of the main goals of MARSAL is to see what it means actually for the ORAN spec and standard. So we did some studies. So if you further zoom in into this ORAN disaggregation and these layers, then you see here all the splits that all of you are probably very familiar with. And I think the main question here is how to see this 7.x split. So in ORAN, it's typically called 7.2, but there are some variants. You have a 7.2a, 7.2b. There's some 7.2c proposal. or even 7.3 splits. And depending on where you exactly split, I don't have the details here in my presentation. Depending on where you split, you do the channel estimation or the receive MIMO processing a little bit differently, and this has some implications on the performance. So roughly speaking, it makes sense to put a low phi on the ORU, the high phi on the ODU, and then the higher layer non-real-time functions on the central unit. But as I said you already before, we have many of them, and we also have these RIC, or these near real-time RIC, that controls everything. And so the question is then, what does this mean for the standard cell-free MIMO algorithms and the performance of our network? So what we did is we started actually our work by looking into the state-of-the-art cell-free MIMO algorithms, and we looked at several options and we mapped them. So we always have this assumption that we have a user here that is served by several ORUs, and these ORUs, so one ODU controls many ORUs, and depending on the clustering, it could be that an ORU that is controlled by a different ODU should also serve a user. And here you see all the different interfaces that matter. And for the ORU, in our initial study that we did already in the very beginning of the MARSAL project, before other categories were proposed, we only focused on the category A and the category B ORU. And then we mapped different existing standard cell-free algorithms on that, if possible. And then we studied the performance with and without ODU cooperation. So for instance, the first option could be, I'm not going to detail all the options, but just to give an example, the first option could be we only do local coherent processing per RU. So every RU estimates and these initial estimates are then averaged. We can have option one without coordination between the ODUs. This means that an ODU only combines estimates from the ORU it is connected to, while if there is an option two cooperation between ODUs, it could be that an ODU takes an ORU estimate from a neighboring ODU to further enhance the estimate for a certain user. In option 3 and 4, we consider also coherent combining at the ODU level, which makes, of course, a better estimation possible. And option 5 is really the what we call canonical cell-free, which means all the antennas in the environment collaborate together to get the best possible estimate of the user signal. To evaluate this, we did not really focus on simulation, but we focused on measurements. So we set up a measurement. We have this testbed. It's a bit difficult to get a good picture of the testbed, but basically here you see two ODUs. So there are two racks with lots of processing power, and you can also see they're connected with many cables to many ORUs here, and of course I've hidden it with my ugly icons, but if you would remove it, then you would see that every ORU here has 8 antennas. So you can see it a bit here. We have 8 antennas, 8 antennas, 8 antennas, etc. And what we do, we have users here, and the users are based on this positioning system, so they can move around. So we can, in a very repeated way, make the users move and position them at different locations. But what we can also do is, in a very automated way, measure many scenarios, right? Because if you would not automate it, every time you want a new scenario, you would have to manually move a user, which becomes a bit boring after a while. So we have automated it, and actually we have in total 256,000 scenarios that we measured already on such a small area. You could notice that this is a bit an extreme area, because how many antennas can you possibly have in a room? This is true, but you could see it as a little bit of the limit of what can be done in a cell-free scenario. We also have measurements in bigger rooms or even outdoor, because as you can see, the cables are long enough to also separate the antennas over bigger areas, and also the two racks can also be separated by a fiber that is 30 meters, so this allows even bigger area measurements. Anyway, for such kind of evaluation environment, we kind of mapped all the signal processing on this 2DU case, and here are the results. So these are the 5 options, and here you see the spectral efficiency for a 10-user scenario. So you could argue that here you don't see 10 users, so we can measure up to 12 users. But also because of these measurements, you could easily combine. Like this user is at 250,000 different positions. If you want to have a 10-user scenario, you just randomly select 10 positions from the measurement database, and you can create any scenario you want. So we created many 10-user scenarios and plot the spectral efficiency for the different processing options. And as you see in this extreme scenario, central processing, of course, is the best. It gives you very good spectral efficiency, even though the users are very close to each other. And you also see that you really need to combine many RUs as coherently as possible, and you also need to coordinate or combine signals controlled by many DU, because if you don't do that, the performance is actually much worse. Voila. We need all users in very densely located scenarios. Voila. So here you see another figure of what we can do with the testbed. So this is another measurement. So MARSAL is not necessarily about joint communication and sensing, but because this is a topic that is of interest today to the research community, I also include a little bit what you can do with this kind of measurement setup, also related to communication and sensing. So first thing you do is, like, of course, online we do the collection of the channels. And because we know where we position the UV, we automatically have very good XY position labels. So it's a no-brainer that we can train a deep neural network for accurate localization. And that localization could then be used, for instance, for research, mapping, user scheduling, etc. But what you can even do extra, and this is another measurement that we did that I show here. What we did here, we put all our 64 antennas on a big linear array, a ULA. But what we did is we made the central antennas transmitters. So we have 4 transmitters here and 60 receivers. So what we have is actually some kind of, you could call it a monostatic radar, but a very distributed one, a very big one, a very big monostatic radar that can transmit and receive, that can transmit signals and receive the reflections. And here you see a small can. It's a very small can. I don't think you would have seen it if I would not have pointed my pointer towards it. And the goal is to see if we can localize this passive reflector, this can. And I need to tell you that the bandwidth of our system is only 20 megahertz and the room size is a few meters. So normally we don't have at all good enough range resolution to be able to localize anything in that room. So you have to see the system as we have 4 times 60 is 240 very bad monostatic radars. And these 240 very bad monostatic radars, they work together. And what is the result? The result is here. This is a measurement result where we can localize and even separate 2 cans with a very good accuracy and resolution. And this is what you could do in cell-free joint communication and sensing, even with many not so high bandwidth radars. By combining the signals in a clever way, you can get very good sensing performance. But I guess all of you know that because most of you are working somehow on joint communication and sensing. Voila. So ORAN and self-remassive MIMO, so cooperation across ODU is a must, and you almost get localization and sensing for free if you have such good channel state information database from your environment. Next thing is I'm going to zoom in a little bit on distributed processing and the Fronthaul and what it means in practice. So if we have this DU cooperation, it's actually almost the same. It's actually the same as what we call sequential processing. So we have many ODU that one way or another estimate the user signals and they collaborate, which means they send their estimates to the next one, etc. And these people have shown in the state of the art that by organizing your sequential processing in the right way is exactly the same as optimal centralized processing. But then what we want to do is not to see how to do the algorithm, but how to implement it and how to implement it in the case where you don't have full precision. And if you don't have full precision, every local processing makes some error that is caused by the fact that you don't have your signals at full precision. Details. I'm just going to show you the results, and the result is actually not surprising, but sometimes we like not surprising results because they show us that things can be done. And these results show that even if we only have 16-bit, which is not so much, and here we have a sequence of 25 access points collaborating, and so this is the optimal infinite precision centralized processing. With this square root algorithm, we converge to the optimal, even if we only have 16 bits. If we do the implementation using the more straightforward SRLS way of doing it, then you see first you accumulate errors. At some point, you still can get to the optimum, but it depends to a large extent on on a lot of initialization parameters. So I'm not saying that these standard implementations cannot lead to the optimum. I just say they're just more sensitive to all kind of initialization parameters, which in practice you want to avoid, because the optimal initialization parameter, for instance, depends on the number of users you're serving, and you don't want to change your algorithm too often if the number of users in your network vary. Good. So we have shown that we need to collaborate across ODU to have a good performance. We've shown that even with 16 bits implementation, you can get it stable enough in a sequential way. So now the last thing I have to discuss is, and I still have a few more minutes, what about millimeter wave? So the MARSAL ID or the MARSAL scenario is still doing something self-free linked to ORAN, as I explained to you before. So in a simplified view on our architecture, we have some ODUs, more than one, and they have to collaborate, and they collaborate using this interface here. And these ODU collaboratively serve a cluster of RU that are serving a user that is somewhere here or here, somewhere in the middle. I did not draw the user here. So we have a cluster of ORU that collaborate together, served by possible multiple ODU. And what is now the question is, can we connect the ODU with the ORU using millimeter wave instead of other more traditional ways of connecting them? Can we use it a millimeter wave Fronthaul? And of course, in MARSAL, we collaborate with Ferrotic, which is an SME, and they're very confident. So they made a recent press release, and they say they have the very first, the world's first viable fiber alternative. So actually, the challenge is really not to get the paths, the connection here, but the challenge is really how to control it. Because if we want to connect these ODUs with these ORUs using a wireless link, then we need to, at runtime, train our beams. So the challenge really becomes the beam training, how to do the beam training. And the question also becomes which millimeter wave radio architecture do we need? For instance, do we need a millimeter wave architecture that can send one beam in the direction of multiple ORU that then receive the same signal and need to do some local processing to change the received signal so that they can do optimal downlink transmission? Or do we need to have an ODU that can send two different signals to different ORU so that these ORU need to do less local processing? So there's a trade-off between the complexity of the millimeter wave radio at the ODU and the ORU, but also the processing that should be done at the ORU. So the first thing we looked into to start answering these questions is really to see how much RF change we need in our millimeter wave solution. So to simplify it, here I have a view. I have M RF chains, and every RF chain gives you a beam and can send a different signal. And per RF chain, I have a number of antennas, and the more antennas I have, the more narrow my beam becomes. So I could have one, if I have a fixed number of antennas, I could have one RF chain with a very precise beam, or I could have more RF chains all with a less precise beam. And this all has trade-offs on how much ORU, ODU you can connect, but also how costly the beam training is. In this presentation, I don't think I have a lot of time left, so I focused mainly on the beam training. So we looked into how to do the beam training, and we saw that actually increasing the number of RF change has not only benefits in the fact that you have more degrees of freedom to connect, to send signals between ORU and ODU, but it also makes it possible to parallelize your beam training and make it faster. And so if I go from 4 RF chains to 8 for the same number of antennas, my beam training becomes a lot faster. Of course, if you, for a given number of RF chains, increase the number of antennas or the number of beams, possible beams, the more antennas you have, the more narrow your beams are, so the higher the beam training cost becomes. Here in this figure, you show though that there's a big performance benefit of having more antennas or more precise beams, obviously, because at a millimeter wave we want to have a good link budget. But also, and it was a bit surprising, the results shows that if you have lots of ODU that do the beam training together, they do create interference. So, and then the more ODU you have, the more narrow the beam becomes, the interference is again decreased. Okay, so one more thing that we looked into, and I think I only have a few more minutes, but I don't need so much time for that, is once you have your beam set up, how sensitive the beam is to blockage. You could imagine in a room a person walking into the beam, but also outdoor you could have a car or a truck passing by, and the question is, can we predict this? And there's this very good paper that actually showed that if there's something blocking your beam, of course you have no performance, but what they have also shown is that the received signal signature just before the blocking is different, and you could predict a blocking coming. So what we have looked into is, imagine that we have a system where we have a main beam sending our communication signal. Could we have also a guard beam that is scanning the environment and tries to predict an upcoming blockage of our main beam? So, and here you see the signature that I said you before. So before we have a blocker in the main beam, we have an elevated received signal. The reason is because of the reflection, we temporarily have a little bit higher received signal power, because we don't only have the line of sight signal, but we also have the reflection. But if we only look at the power of the main beam, the time, this is really just before the blocker occurs, and maybe our network does not have enough time to trigger a handover or look for another path. So what we did is to see, could we have a main beam, a guard beam, I mean, that is pointing next to the main beam, and this guard beam can then maybe detect the blocker a lot earlier in time, so we have enough time to do a handover or whatever we need to do.
One more minute for this talk, so sorry for.
Okay. But I'm really almost there. So the thing I wanted to show is that it works. So even in measurements, we can predict. We can predict the blocker ahead of time. So even up to 360 milliseconds, which is, I think, enough to do something at network level. Voila. So this was then my conclusion and takeaway. So I talked about ORAN opportunities for self-remassive MIMO. So I've shown that we can map standard algorithms on the ORAN architecture. And the main challenge is to optimize not only the performance, but also the costs of the information that has to flow between all these elements. I did not detail that in the presentation yet. We can, for free, get location estimates easily, and that can be used for physical layer aware scheduling. And X apps beyond communication, localization, sensing are very important. And then I talked a bit about millimeter wave. So I've shown that the beam training is costly, blockage is likely but can be predicted. And the millimeter wave benefits for self-MIMO are the fact that we have a flexible architecture, so we can dynamically decide which ORU to connect to which ODU. Voila. I think there are no time for questions, so I apologize for that, and thank you for your attention.
Thank you so much, Sofie, for a nice overview of MARSAL view on this topic. So certainly, distributed MIMO is an important key component of 6G, and of course, ORAN is only one possibility for realizing that. So and it was very nice overview. There are a few questions that it would be great that we go through offline. So for the sake of time, by this I would like.
If I may just say also one thing for this predicting the blockage, so that was also certainly interesting part. And with respect to predicting, there are also certainly other possibilities and other information that might be available via some other sources. For example, if you have some cameras in if it's an industrial area, you anyway have already cameras, so you could use information from there or so on.
Yeah, that's definitely a very good point, and we indeed have to see which way of doing it is the cheapest, because having an extra beam, the guard beam, might also have a cost, and maybe the camera is a cheaper solution in the end. I agree. Yeah.
Yeah, and exactly. So the point regarding the cost that you mentioned, so it seems that and so it seems very important to be cautious about the cost implications of different type of solutions or architecture here. And so it's definitely an area to investigate more. And
yeah, we need to think carefully, not only the cost in terms of hardware, but also the cost in terms of power, because the fact that you just put a beam there, which is costly in terms of power, right? Just for predicting a possible blockage, you might want to reflect about that, if that's the way to go. But yeah, in some scenarios, probably it's good. If you have very critical communication, then maybe it's worthwhile to put that extra energy and hardware cost, but maybe not in all scenarios. Yeah.
Yeah, thank you for sharing the insights and the discussion. So I very much appreciate it. I think by this we can move on to the next seminar from REINDEER project. So, Fredrik, the floor is yours, please.
Yes, thanks a lot. And I hope you can pin me my video centrally your side for everybody.
Yes, so I made your video spotlight for everyone. So let's
okay,
see.
I see only you, but that's maybe on my, yeah, now I see only you on my screen, but that's maybe only on my side.
Have you already shared the slides or?
Yes, they are, I mean, I have them embedded in my video, so they are there.
Okay, Mikko
can see Hamed in video and Fredrik in video, but the slides are only partially visible behind Fredrik.
Yes,
they are behind
then
Fredrik.
it's as it should be. So thanks. It's
yes.
Just I had another view in Teams. So welcome to this presentation then from REINDEER on experimental database channel modeling for distributed massive MIMO. So my name is Fredrik Tufvesson from Lund University in Sweden and working in the REINDEER project. Compute and storage resources in the environment. With this, what we get is that we have, I mean, also supporting very local communication. So a lot of the communication is actually quite local, and so it doesn't have to go centrally and then back again, but it can stay there. What we also get is very high diversity. So we have an enormous amount of diversity, which means that we always will have a reliable communication and with very low latency. What we also have is that we have proximity. So we always have some radio units close to us, which means that by that we can also both communicate with the energy neutral devices, and we can also reduce the amount of energy that we have to transmit and the power that we have to transmit. And finally, redundancy. There are always antennas available, radio units available, which means that we will have a very, very reliable connection in this case. So looking at from a theoretical perspective, if we take this radio stripe concept that Ericsson has presented, and then we do it so that we have several stripes in a room like this. This is a pretty large room. And if we compare and look at the energy efficiency and the amount of power that we have to spend in order to create reliable communication, then we can see with the many antennas, then we are going here and we can reduce the energy a lot. Of course, it's link energy that we're talking about. We should also consider the processing energy, but just spending, focusing on the link energy here. Of course, then we have the problem or the question, what about reality? Do we actually, can we get those gains also in reality in real setups? And therefore we have done some investigations, some measurements where we try to emulate what would such a radio wave, how would it look like, and what are the channels that we see in such setup. So here we're really focusing on the lower frequencies, meaning below 6 gigahertz, because there is where we think we can have both the coverage as well as the energy. If we want the really, really high data rates, of course, we maybe should go up to millimeter wave or above. What we have emulated here in reality is a radio wave with many, many antennas along the walls here. So we have covered the two walls, one 3.5 meter wall and one 9 meter wall with antennas. So in total, we have an array here. It's a virtual array of 15,500 elements there. It's half a wavelength spacing between antenna elements along the length there, and it's measurements at 5.6 gigahertz with 240 megahertz of bandwidth that we see here. If we take a look at the measurement results, and then we have different user configurations, the dots that you see here. I mean, there are different cases where we have gathered the users in a small spot, or we have distributed them, or we have them along a line in one or the other direction, and we see different properties. And in reality, there we go. In reality, this is how it looks like. So we have an environment, indoor environment. It's a fairly big room. We are measuring with the Lund channel sounders that we are triggering, and then we have created this virtual very large wall there. As a UA, we have those monopole antennas on the ground plane. So omnidirectional antennas at the user side, and then we have patch antennas at the weave with an opening angle of plus minus 60 degrees or something like that. The users, they're distributed like this, so that we either have them parallel, we have them perpendicular to the main wall, can be dense, but with a random placement. We are trying out with the widely spread users as here, and then we have the body shadowing, so that we are looking around the body and how that would influence the channel that we have there. We also see this blocking object, the shelf over here, and that is in some of the measurements. And with the high diversity that we have, then we will see that the influence of such a blocking object is not severe at all. Maybe I should. So if we start looking at the received power levels that we have there. So the wideband radio measurement, we look at the power levels for two different users. And as you can see here, we have user 1 here, we have user 2 here. For the widely distributed setup. And you can see here that we have quite large variations in received power levels. So of course, the antenna elements closest to the users, they are the ones that are really effective. And we can see that actually we gain a 30 dB or something like that compared to the main user. If we have a look at the other user here, of course, it's another set of antennas that are more effective there. And in reality, what we should do is that we activate the effective antennas for this user here, and then we affect and activate the antennas for this user down here, so that simultaneously we have good antennas for all the users. And then we're trying to find this subset of antennas that are effective for each of the users. What we also can see here is that we do have some fading, even in this clean line of sight situation that we have here. Of course, there are scattering in the room, so which means that we do have some small scale fading around us. And we have variations, not just because of the influence of the antenna patterns that we have there with those stripes that we have over here. So if we look at the received power levels for all of the antenna elements, we can see that even with such short distances as we have here, up to 9-10 meters, we do have a lot of variations in received power levels for each of the antennas. And it's a combination of both the influence of the antenna pattern itself. We have the interaction with the user and the environment, and we can best describe this as a gamma distribution, and then we have large scale fading, which can be well described by a log normal distribution. And depending on the scenario, we of course have different variations or different variances for that log normal distribution. If we now try to take all those antennas and then we really focus the signal energy to the users. So now we have those 16 users along a line, and then we try to focus the energy towards each of and every one of them. We see that we do have a large, very small leakage from one user to another. So in this case, what we see is how much, if we focus to user 7, for example, how much of leakage do we have into user 6 or 5 and so on. And we can say that there is almost nothing there, even though that they are separated very small distance from each other. And this is due to the large focusing effect that we have when combining the antennas coherently and really focusing on where we have the user antenna. Let's now also look at what happens when we have a dynamic channel, so that we, and now we pick some of the antennas in the wave. So in this case, we have 12 antennas that we study in detail in the wave, and then we have a user moving along this red line here across the room. And then, of course, at the beginning, we are close to one antenna or two antennas, 3 and 4 here. And then when we move, we get closer to other antennas. And of course, we get some power variations when we have a dynamic situation like that. We also should notice that we have this shelf in the middle that is either there or is not there. So, let's see what kind of influence we get from such a blocking object in this case. If we just, of course, first, this is how it looks like in reality. We have the distributed 12 antennas here. We have the UE down here with its ground plane, and it's running around along this red line there. And if we study how the channel evolves over time, so here we see the different links from the UE that is moving to the 12 antennas that we are now studying in the radio wave. And we can see that very big early over here. Then we have some channels that are very effective. They are close to the UE, and of course, they are the ones that really should be used for that particular UE at that moment. Later on, we get other antennas that are more effective, and of course, we should put our attention to them. And if we do a good combining, then we reach this, what we see here with the MRC, we're using all the antennas, that is seen as an upper bound of what we can achieve if we combine all these signals coherently from the 12 antennas that we are studying now. That is the power variation that we have. And we can see that we have a very, very good and stable channel. Of course, still with some variation, but that's due to the very close distances that we sometimes have. If we now look at the same thing, but with obstruction, then we can say that there is not a big difference. Of course, here in the middle, where we have the blocking object, we can see some influence on the individual links, but overall, there is always sufficient number of antennas that provides a good line of sight to the user, so that we actually can, the effective channel that we have is very, very stable and very efficient from an efficiency point and energy point of view. Now, this was for clarity, looking at this large-scale behavior. If we take and look at the instantaneous values, this is how it looks like. We have the same underlying behavior there, but we do have much larger variations due to fading effects. On the other hand, when we then try to combine signals coherently, and especially if you look at this combined version, the red one there, you see that the small-scale variations, they are more or less gone due to the massive MIMO and channel hardening effect that we get in this case. This was with no obstruction. If we look at the case with obstruction, similar with slight variations, but very similar overall. So let's now also go to another very interesting case, and it's when we do sensing. So as described by many of the other speakers, we both have the monostatic radar channel, but we also have the bistatic or multistatic radar channel, which means that all the receivers that are not transmitting, they can listen, and they can listen to the signals sent from other elements being reflected on an object and coming back. So this will give an idea of both how the environment looks like and also what is happening, what are the dynamic parts of the object and in the environment. And let's look at this object. Now we have a human going along the same line as we went before. We have parked the UE number 13 at the static position there. So the only thing that is happening now is that we have a person walking in this environment. And this is from, if we look from node 1. We will have another example if we look at node 5. Then we have another set of link combinations. So we we receive the signals from all other transmitters there. It's transmitted, it's reflected, and there is possibly also a line of sight between the transmitter and the receiver 5. And then let's look at those channels. And if we start with node 1, this is how those sensing channels, the multi-static radar channels, actually look like when we have a person walking there in the environment. And if we start from the top, there we have some line of sight channels being very, very close to each other and with very little interaction. And the scattering from the user is actually quite small in relation to the direct power or direct signal that we receive there. So we see not so much. But if we take some other links here, then we can see that depending where they are, we get more or less influence early or later. So already there we can say quite something about where are things going on, what is happening. And if we look at the details there, we can also figure out exactly where this thing is happening. This was from node 1. If we now switch to node 5, then you see that we have another behavior. So here with node 5, then we have blocking of some of the stronger links that we have there. And then for some links, they are quite stable. Something is happening in the beginning, something is happening later on. And by the combining all those combinations between all the links, we actually have a very, very good radar system at our disposal that we can use for joint communication and sensing. Again, these figures I showed here, they were for the large-scale fading effects. If we look at the instantaneous channels, this is how they look like. And here is where we have all the details and also can figure out what are the small movements that we have there. This is from node 1. And if we look at node 5, this is how it would look like, or how it looks like. So let's now take another step. So our colleagues in Graz, they have also measured one thing, and we have done ultra-wideband measurement where we did a large virtual wall with ultra-wideband measurement capabilities. So we are scanning this wall there, roughly speaking, 2.5 times 1.6 meters. So it's quite a big wall. And then it's all coherent ultra-wideband virtual measurements that we are doing there. And then we have different transmitters in this environment. So it's a somewhat smaller lab room that we have there. And then we can see how the signal propagates from the transmitter to this large radio wave that we have there at the wall. So this is the case. We have the transmitter there in the middle. It's line of sight. It's more or less an empty room. We all sometimes have a shelf there. And what's really interesting is now that if we look at, how the impulse responses, how they evolve over this large surface that we have there. So what we have selected here is one row or another row for two different user positions, one user position over there, one user position over here. And you can see that, well, shadowing effects, they are not there, but what is happening is that anyway, signals are coming and going. Signals and scatterers, they are not visible over the whole surface. For example, you can see the two circles over there. There, at one row in the wave, we can not see a particular scatter, but at another row in this wave, located just 0.5 meter down, we can see this scatter. What we also can see here is that we have the spherical wavefront effects, because everything basically from an antenna perspective and array perspective, everything is in the near field. So we do have variations over the array, both in received power levels, as we saw before, but we also have it then at individual scatterers. They are not always visible over the whole surface. And let's now look at an illustration where we have taken the impulse responses for some selected delays or propagation distances that we have here. And then you can actually see very clearly how those wavefronts, how they look like and how they evolve over the large array that we have there. So in the first row, we have a receiver transmitter straight in front of the large receiver, and we can see how the wave propagates, and it takes longer and longer for it to reach the outer elements in the wall. And then we can also see some scatterers that we have over here from the window, and we can see some other reflectors over here. Second row, there we have another transmit location, and we can see that we have a spherical wavefront, but now coming from another direction. And it becomes more clear if we now look at it. Now it's a little bit small, but you can see the two cases here, and now time is running. So here we have a propagation distance of 2 meters. Here the signal is coming from the first transmitter, here it's coming from the one in the middle, and you can see how the spherical wavefront, how it evolves over time. Here comes the reflection from the walls, and yeah, we can look at it more in detail if we take this one time again. So we have the transmitter at position 1 there. It's 3.5 meters from the receiver. So now something starts happening. There it's coming, and there is the line of sight. Here is the wall and ceiling, or ceiling and floor reflection. Here comes the reflection from those windows. And then we have a reflection coming here also from the back wall after 9 meters. Here we have the back wall reflection coming, and you see that is coming more or less at the same time over the whole area that we have here. So by looking at those signals that we have there, then we can identify where are the scattering coming from, we can use them as virtual transmitters in order to locate where do we actually have our user. So to do that in practice, what we can do is that since the signal statistics are changing over the array, what we're doing is that we divide it up into subarrays. In this case, it's 8 by 8 subarrays, and we are using a 500 megahertz bandwidth. In this case, at 7 gigahertz. And then we are located, where do we have those virtual sources in this map? And then we can see that, okay, here, that's the wall reflection. Here's another wall reflection. There we have the direct line of sight channel, and so on. And with this, we can then use this in order to locate other things inside this room. We have not only done it in this lab environment, but we also have done those measurements in a larger hallway. And to have a description and model the channel we are proposing, I mean, there is a deterministic part given by the environment, and that is where we really have the location information and the information about what's going on related to both the environment as well as to objects within the environment. And then we have the more stochastic part, and that stochastic part, or dense multipath, it's a bit hard to use from a sensing perspective, but it's very good from a communication perspective in order to really distinguish different users from each other. And that's also true with the deterministic parts, because the deterministic parts will be seen differently from different users. So to conclude and to summarize, so we have been working on this radio wave concepts, and it's really ensures that there are always a set of efficient radio elements to provide services for each of the users. And this concept, I mean, whether we call it radio waves, large intelligent surfaces, distributed MIMO, or cell-free massive MIMO, I think it's a logical next step when it comes to enabling the increased reliability, energy efficiency, and sensing capabilities. I think it's very promising, all this multi-static capabilities, radar capabilities that we have there are very promising from a sensing point of view. What we should remember is that the radio channel is seen differently at different radio elements. Scatterers and reflectors, they have a limited spatial visibility. We do have a spherical wavefront effect there. So if we want to describe this by a model, so then we should really have a spatially consistent model with deterministic components given by the geometry or a random geometry, but they should be there in the geometry, and then it can be used both for communication and sensing such a channel model. And with this, I would like to say thanks, and the details, they will be in deliverable 1.2 that we have been working on, just submitted it. It's not yet public. It will take some time until it gets public, but all the details are there. With that, thanks a lot.
Thank you so much, Fredrik, for sharing some insight. Very, very interesting presentation and very interesting result. It is great to see the potential for this kind of technologies, not necessarily at high band, but also at the mid bands. This kind of massive antenna technologies could be of benefit, so both for sensing and also communication. As far as I see, there is no question raised so far, but a question that I have is related to the sensitivity of these kind of systems to different type of impairments. Can you elaborate a bit? How is the situation compared to, let's say, centralized MIMO in this case, if you want to compare?
Yep. No, so one key thing is coherency. Everything relies on having coherent transmit and receive elements there. The good thing is that you can solve many of those things by over-the-air calibration. So you can have local oscillators that are slightly drifting, as long as they are not drifting between your over-the-air calibration instances, you are quite fine. And that's also an advantage when we go distributed like this. It's easy to do that at the lower frequencies, because everything relates to the bandwidth, and now we are having bandwidths in the order of 5 to 10 centimeters as opposed to the millimeter wave case. There it's more tricky to do this distributed combined transmission or reception, unless if you have a centralized approach with fiber connections doing everything coherently. I think you could solve it also in the millimeter wave case, but that's, I think, is to be seen in the future.
Yeah, great. Thank you so much. If there is any other question in the hall. And maybe as another question, so how much do you think this kind of technology would benefit communication versus localization and sensing type of use cases? Is there any insight here?
Yeah, I think, I mean, they go a little bit hand in hand. There are many, just from a communication perspective, I mean, there are many benefits in terms of reliability and energy efficiency. And then I think the positioning comes a little bit, and sensing comes a little bit for free. That it is, I mean, once you have those distributed antennas there and the coherent signals, you don't need special waveforms for the sensing part, but you get them for free. Then, of course, when you have positioning, then you can also do like a predicted and predict which antenna elements to activate in the future when you can predict mobility of users and things like that.
And that could be for possibly further energy enhancement, maybe.
Yes, and especially in order to reduce the computations and make sure that we are only focusing on the very efficient radio resources that we have there, and then we can deactivate the not so efficient radio resources.
Yeah, thank you so much, Fredrik, and we are looking forward for the deliverable of the project.
Yes, thank you.
Thank you. I think by this we are set for the next seminar. That would be from RISE 60 project. George, if you have George online. if we have George Alexandropoulos from RISE. I'm not sure if he's already in the meeting.
In the list, I don't also see him at the moment, so not sure what happened there.
And if we have someone else from RISE 6G, it's perhaps we can wait maybe one more or 2 more minutes, see.
Yes, anybody from the RISE 6G project in the call?
I haven't received any message from him, so
Also, I don't have any information, so I hope he's fine. Don't know.
Miko Ahmed, this is Mauro from Telecom Italia. I have written to George an email, so let's wait probably a couple of minutes to see if he may join us.
yeah, great. Thanks, Mauro. There might be something unexpected happens. But yeah, it's so far we have seen a good overview of different radio components, channel modelings, and enablers for both sensing and also radio communication. So it was an interesting overview so far. And by the time we have George online, if there is any questions or from presenters or any general question, please feel free to share. Yes, Henk, please.
During the waiting, I can have a question to Fredrik. When you do the array assumption, you always assume is the half-wave space, right, between antenna elements in the array, right? Fredrik?
Do we have Fredrik online? If so, we cannot hear you yet.
Maybe he's not at the place.
It's possible that he already left the meeting. Do we have Fredrik from REINDEER online?
Yes.
Hi, Fredrik. Yeah, it's in here. I have a question to you. Sorry.
Please go on.
Yeah. So you always assume the antenna space in the array space is a half wavelength, right?
Yes, but to be honest, we don't use the fact that they are half a wavelength spaced, but the beamforming is done on a reciprocity-based assumption that we use the uplink channel estimates for the downlink transmission as we do in reciprocity-based MIMO. So there is no active beamforming to specific directions in this case, and that is also how we handle, for example, spherical waveforms and so on, that we are just using the uplink channel for downlink transmission.
Okay. Okay. Thank you.
And thank you for the question and the answer. So we're still waiting. Yeah.
While we're waiting, I mean, I think that's a thing we also could think about and discuss. I mean, the explicit beamforming versus the reciprocity-based beamforming, where is actually a limit for it? We need it at the higher frequencies. When do we actually need it? And especially when going to those, call them centimeter band between 7 and 20 gigahertz. Do we need?
Yeah, exactly. That's the question. High frequency is very difficult to keep those limits for the half wave, right? So what is the impact of the larger space between antennas or antenna subarrays? So that could be interesting to study. Yeah.
And well, Hamed, I leave it to you.
Hamed, sorry to interrupt you. I've contacted the RAI6G coordinator, and he's calling George. So possibly let's wait some other couple of minutes.
Great. Yeah. Thanks. So yeah, we can wait a few more minutes. Sorry everyone for the inconvenience. So we hope everything is fine with the George, and so we could have him online.
You could try to call George from Teams here, so he connect directly to the meeting if he's at his computer.
Yeah, sure, we can maybe try that. So. Yes, we have George online. Hello, George.
Hello.
Hi, George. Welcome to the seminar. So
you can hear me and you can see me, right?
Yes, we can see you and hear you very well.
Apparently, I was waiting on the wrong link. Apologies for that.
Okay, so sorry for that. So it's great to see you the right meeting, then yeah, we are very eager to see your RISE 6G view and have your seminar. So please feel free to share your slide.
Yes, okay. Just give me a moment just to be sure. Please tell me if you can see my screen, and I'm ready to start right away.
Yes, it is clear. Please go ahead.
Okay. So thanks for the invitation. Hello to everybody. So I will present you actually RISE 6G's view on the localization, sensing, and actually their integration using the key technology, which is actually being elaborated within RISE 6G, which is actually called the Reconfigurable Intelligent Surfaces. Before going into the exact details of what we're doing within RISE 6G, let me just spend a couple of minutes just to tell you some things about the consortium. Actually, RISE 6G is actually now in the third final year, has started, a couple of days ago, of a 3-year duration, 3-year journey, and the consortium is comprised of 7 educational and research institutes. You see there, CEALETI, CNIT, CNRS, Aalborg University, Chalmers, University of Athens, and University of Nottingham. We have actually 4 manufacturers, telecom operators, and technology providers, NEC, Orange Team, and the SME Greenerway from France, and 2 big verticals, actually CRF and SNCF, which are about to provide the fields to demonstrate actually the envisioned things regarding the application of net technology for boosting actually communications, localization, and sensing applications. So in a nutshell, the project is actually elaborated.
Sorry, George, before you continue, there is a part of the teams that overlap with the slides. So in your screen, there is a small box of, yes.
Sorry. I didn't know that you see it as well. I thought it was only for me. Okay, so thanks for clarifying that. So in a nutshell, RISE 6G is actually shaped around the technology of reconfigurable metasurfaces to enable smart radio propagation environments. And actually, what is a reconfigurable intelligent surface? A reconfigurable intelligent surface is an ultra low power surface comprising metamaterials whose responses can be electronically controlled. It's actually a new type of system node, actually, whose element responses can be adapted to the status of the propagation environment, requiring, of course, either implicit or explicit control signaling. The idea is that up to now, we had the capability to optimize the transmission and the reception, but the environment was actually passive in the sense it was something that we cannot really influence, could not really impact, because it's being determined by the geometry of it, and signal propagation depends on the obstacles within the environment. So the idea with this technology is to code certain obstacles of the environment, enabling the capability to have reflections, propagation of the electromagnetic signals over the air in ways that we could program. So the overall idea of RISE 6G is actually to optimize jointly the transmission, the reception, and the propagation of the signal over the air. Of course, in order to do that, we need to design and control RISs. Actually, in the project, we're working on multifunctional RISs. You will see details later on, apart from the initial proposal, which was mainly for smart reflectors. And the idea is to use them, to deploy them, to enhance wireless communication, but also localization, sensing, and whenever possible, their integration. So in a nutshell, the project's vision is to design, prototype, and trial radical technological advances in order to forge a programmable wireless propagation environment. We're working actually on for an all-in-one architecture to seamlessly integrate the existing elements of current networks, but of course of 5G networks, but of course incorporate also the new technology of metasurfaces. The idea is to devise low complexity and easy to install hardware regarding the metasurfaces. Of course, it's critical to orchestrate them in an efficient way. And of course, at the end of the day, we're targeting an overarching prototype in different frequencies, ranging from typical cellular frequencies up to millimeter waves. So the idea is to include a new layer, this layer 0 as we call, which has to do with the signal propagation, to be jointly optimized with layer 1, right, for various objectives, realizing, as we actually call it within a project, performance boosted areas that can have quite diverse and many times contradicting requirements within very close geographical, regions that can be, however, accomplished with also with this enabling technology of the over-the-air signal propagation. I will go very briefly into the preliminaries of localization and sensing. I'm sure that this has been covered before. So localization, as you know very well, is the process of determining the two-dimensional, three-dimensional location of connected device based on uplink or downlink measurements with respect to several base stations. It can actually happen with using round-trip measurements based on a downlink angle of departure measurements, or even using dedicated functions within the 5G terminology. In general, positioning requires reference nodes with known location and orientation, time synchronization between the nodes that actually are included within the process of localization, the so-called reference nodes. In principle, we require pilot signals either in the uplink or downlink to measure them in the receivers, and of course many times to fuse the measurements to compute the UE position. Various metrics related to localization, the accuracy, the latency, and the availability, which actually determines the fraction of space or time the service is available with required accuracy and latency. And apart from localization, there's also the sensing, which refers to the detection and estimation of changes or events in the environment, including for use in positioning. There is this radar-like sensing, monostatic or bistatic, and the non-radar-like sensing, which actually refers to activity monitoring and challenge sensing. Now, regarding RISs, so there is a couple of, I would like to go through a taxonomy we have been working on within the project. Actually, there are a number of other forms of RIS, but I want to emphasize on this specific two, which are the subject technology that we're working for localization and sensing. So the first one is the reflective reconfigurable intelligent surfaces, which are comprising of passive elements, meaning that the only power that is being used there, the only circuitry that requires power, is the circuitry that changes actually the responses, the electromagnetic responses of the elements in order to actually tame the reflection of the signal that impinges upon the metasurface. And actually reflective RISs, they reflect the incident signal in a controllable manner. In practice, we have current actually fabricated RISs, low resolution in terms of the phase states, which at the end of the day translates to the reflection coefficient that we can provide in the impinged signal. We're also working, which is something that actually popped up within the project, on this concept of hybrid reconfigurable intelligent metasurfaces, and the hybrid actually has two meanings here. Hybrid in the sense that they are both the so-called passive of reflective, but also some active elements enabling the reception of certain of characteristics of the impinging signal in order to be available in baseband. So the RIS is capable to collect some measurements to perform certain tasks, for example, sensing or channel estimation. But apart from that, the hybrid goes to the simultaneous operation that this hybrid RIS is providing, which we have designed actually dedicated hybrid meta atoms that they can sense, meaning feed a portion of the impinging signal to a reception unit, which we can use, for example, to collect some baseband measurement, but on the same time, they can reflect another portion of the impinging signal with a tunable way. So these are the hybrid meta atoms, and this simultaneous reflection it was initially proposed to actually speed up the process of channel estimation of hybrid RISs, but it can be used, of course, for localization and sensing, either as a standalone operation or as an operation that is being used to optimize the physical layer, this so-called sensing adding the physical layer communication. Okay, there is actually also an extreme version of this hybrid. Can have these two extreme versions. The one extreme version is to be fully reflective RIS, meaning that no portion of the impinging signal goes to baseband, to the reception unit for correlation. The other extreme is just to use all the impinging power, right, of energy of the impinging signal to drive it, to guide it in baseband for measuring certain characteristics, and this is called the receiving RIS that you will see later on. So within the project, we're actually working on two dedicated ways of using an RIS for localization. The one is to enable localization, meaning in cases where without it you couldn't localize. For example, there you will see scenarios where we have been working on providing localization even without the existence of any access point. But also the other way of utilizing the technology is by improving the localization performance of an existing localization systems. In this way, RIS can act actually as infrastructure, providing this additional degrees of freedom to enable localization. But many times, as you will see later on, there are certain cases where we're also seeking of localizing the actual RIS. For example, in application where the RIS is coding actually a car and we want to localize a car. The challenge within the project is, of course, to devise architectures and different problem variations, the control strategies, which is really critical. And there is actually a chicken and egg problem with the capabilities that the RIS can have. For example, consider that if you have a full, nearly passive RIS, of course, every time an RIS has a controller, right, that is capable of communicating with the rest of the network, taking the orders in order to change the configuration. But if we enable it with some sensing capability, of course, this will impact the control. We have been working on various methods for localization, and of course, the attainable performance. In order to do that, we have actually worked both with synthetic, but also with real data, something to be more pronounced in this ongoing last year of the project. So we have defined 5 distinct architectures, corresponding localization and sensing scenarios, and corresponding data flow and signaling. So the architecture for the 5 scenarios that we have is: number 1, on the left, you see the RIS-enabled localization with angle only requires at least 2 RISs, or angle and delay measurement where 1 RIS is enough. And the idea is to use this scenario to localize a device with only 1 single antenna base station. Another scenario, number 2, is the RIS-enabled localization without access points, where we're targeting and localizing a device without the intervention of a base station, neither a collection of from the side of a base station or the access point, or an access point. Scenario number 3 is the receiving RIS to detect passive users, performing sensing, detecting users without a base station. Scenario number 4, the hybrid RIS-enabled localization without access points, where again you can have localized without the base station, and in this case you can do it even in narrowband scenarios, in contrast with scenario 2, where you will need wideband operation in order to do that, to enable this time difference of arrival as measurement to utilize in order to perform localization. And the mobile RIS localization, which is the last scenario that I've been using, where the idea is to localize an RIS. Going a bit deeper, you see here this RIS-enabled localization with angle only and angle delay measurement. It requires an RIS with time-varying configuration, knowledge of RIS configuration and response. This is actually a requirement, the knowledge of the RIS location and orientation as well, and we require a coarse synchronization between the UE and the RIS. You also see here in this slide the data flow and the architecture. I will give some details on the architecture. So there is the need, of course, for an RIS controller, which is actually associated to a single RIS device. In principle, you could have a controller actually controlling various RISs, and the controller can be actually part of the RAN, can be part of a RAN element, or they directly interact with a RAN element, either a GNB or an ENB in 3GPP jargon. And in addition, it may directly interact with ORAN near RT-RIC. Expected time granularity is in the order of 10 to 50 milliseconds. There is also the need in this architecture for this RIS orchestrator, which is placed on a higher layer and orchestrate multiple actually RIS controllers and/or RAN elements, and it can directly interact with the other orchestrator, right, within the 3GPP jargon, and the time granularity is expected between 100 milliseconds to a few seconds. Regarding the risk control, which is a critical thing, this is actually the goal of the risk controller. So this controller requires external information to determine the risk configurations, either in the form of channel state information, or in the form of location information, or in the form of sequence of predefined configuration. From a code book, you will see later on various code books, reflective beamforming code books that we have been working on. Definitely the risk configuration should be optimized for the position or sensing, or an integrated, right, a simultaneous operation, accounting for the possibility that the environment could have other RISs as well, could have base stations, or even specific properties of the RISs, for example, specific dedicated hardware impairments. So within the project, we have been developing and analyzing several RIS control strategies. Number one, the basic risk configurations, beams that are directional, derivative, multi-beam, random configurations, where in certain times it can do the job, especially for when the application is communications. The risk configurations optimized together with a base station precoding, risk configurations suitable explicitly for near field positioning, and configurations that account for risk hardware models. Now, going to those configurations, you can see here this basic beam types. From the left, we have the directional, where the width can be controlled by switching of the elements. It can provide immediate angle of arrival indication, and can exploit prior UE location knowledge to reduce the resources. The derivative generates nulls in certain direction, and it actually has been shown to be optimal for localization with accurate prior UE location information that can be actually be available from another subsystem actually that is there to support this specific operation with the RIS. Random configuration, where there is no directionality, they cannot really exploit prior location information, but on the other side, they can cover the entire angular span with few RIS configuration, and in certain cases, it could be the right way to go when we're thinking about initial access. And of course, there are also the multi-beam configuration, where the idea is to illuminate several directions, either in a static or in a dynamic way, but of course the gain would be reduced. Going further to another scenario, this risk-enabled localization without access points. I just want to emphasize here the requirements. In this case, there's no access point or base station. The idea is to localize without a base station by using an RIS. In this case, we require a full duplex UE in order to have the degrees of freedom to perform localization. There is need to have time-varying configurations. The knowledge of risk configuration and response is actually a prerequisite within the system. Also, the UE, in this case, the UE is going to do the job to perform the localization algorithm. The knowledge of the risk location and orientation is something that is needed as well, and we require a core synchronization between